Alright. So what we want to be able to do now is expand upon this. If I want to be able to find the surface, the area of one of these discs that gets laid in our pattern, how would I go about finding the area of one of these discs if I know this is a relationship for the radius of that disc? Yes, sir?
You take the y value and then square it times it by pi.
Well, in other words, take this r of x and square it times it by pi. Is that what you're telling me? Because that's the y value?
Yeah.
Okay. So the area of a circle as a function of x is going to be pi times capital R squared of x. We did that in bell work. Right? Okay. So that's one disk. How am I going to find all of them combined together? Yes, sir?
You take the definite integral of the whole equation, and then in the range you got, and then take that number squared times pi.
So something like this, right?
Yeah.
Now, the reason we're able to do this is the definite integral is based on the summation concept that we had back in chapter 4. So in essence, we are just taking the summation of all these different things. But this allows me to do a much more accurate job of the summation instead of having a series of things like my little example pattern, which had varying layers and it wasn't a smooth curve, it had these distinct values. This allows me to get a smooth curve. Now we are going to translate this into a form that makes it a little more usable for us. The book kind of shows you it this way, and I've seen it this way most of the time. Volume equals pi times the integral from an a to b, start to end points. An area function includes the r of x when that quantity is squared, dx. So that form there is really probably what we're going to work from. And you'll notice that that form there includes pi on the outside of the integration. It is just a constant. You don't have to worry about integrating. So this is the formula that we're going to operate from.
So it would be 1/3 r to the third?
Are you trying to work on the example we had?
No, I'm just trying to do it.
Oh, this is all dependent on what is the function that is r. So for us, in our example up here, what is the function specific to this setup that is my r of x?
Well, the square root of x.
Yeah, it's just the square root of x, basically minus 0. So if I come down here and look specifically, I say the volume is equal to pi times the integral. We'll get the endpoints in a second. The square root of x minus 0 is my radius length squared dx. And yes, I realize that that means it's just the square root of x squared. What are the values for my interval?
A0.
So 0 to 4. Does that make sense, everybody?
How'd you get that?
Okay. Based on the information listed right here. The boundaries I've got are the square root of x and 0, which is this x-axis. So right there's my radius. So this one minus this one. That's my r of x. Then these x's between 0 and 4, these are my boundary numbers, my interval numbers that are here and here.
Okay.
Question?
So can we just simplify that to be the integral of x?
That would be the plan.
Okay.
So something like that. Now can we integrate this?
Yes.
Well, I hope so. What do we get?
1/2 x squared.
So 1/2 x squared times pi, or 1/2 pi x squared, or pi times 1/2 x squared. One of those three, because it's all multiplied, it doesn't matter. We plug in the 4, we plug in the 0, we evaluate, and does this become 8 pi units cubed for a volume?
Yes.
Questions about this?
Where did that 1/2 x squared come from? I mean, the step before that.
That's the integral of x dx. Remember, that's x to the first. So we increase our power by 1 and we divide by that power.
How did you go from the thing above it down to there?
Just to here. What's the square root of x minus 0?
That is square root of x.
But then I square it because the radius is squared.
Oh, I forgot those.
Yep, you got to remember to square it. Yes, sir.
Why can't we get the definite integral in the problem and then do the pi r squared rule?
Based on our order of operations, we have to multiply this out first, square this out before we apply integration. Just like when we did a summation problem. If you have a summation problem that looks something like this, I equals 1 to n of 3 minus 2i the quantity squared, you have to multiply that out first, then apply the rules of the summation formula gives me this for an I, or an I squared, or just a constant number. So we have to multiply it out before we can add. That's the same rules applying from there to there. Other questions about that? Did you go back up a little bit?
Yeah, sorry, I was too busy playing with
There's that part. Oh, I didn't. What I want you to do is I want you to determine the volume of the object formed bound by f of x equals x squared, y equals 0, x equals 0, x equals 1, rotated about the x axis. We'll start there. And I want you to kind of work on this on your own just a little bit. See how far we get with this. We'll use the same boundary set to do a couple other things.
I have a question
Mm-hmm.
about distributing the square. Can I just... X squared is on the inside of that square. Can I just make it x to the 4th?
Mm-hmm.
I didn't think I could do it. Thank you.
Thank you. Okay.
So is this the reason that you got?
Wait, so that's minus 0? Why is it minus 0?
Because remember, 0 is this equation right here of the axis of rotation. So I'm going to go from this upper boundary edge down to the axis of rotation, determine the size of my circles that I'm generating. I go a little fast there.
Is it still squared?
Oh, that is a 5. Yeah, I went a little fast there, didn't I?
Ah, that makes sense.
Yes, it should make sense now. Sorry about that.
Good.
Questions about that?
This is just a question in general about exponents.
Yes?
When are you supposed to multiply exponents and when are you supposed to add exponents?
Okay.
In
Well,
this equation, it doesn't matter because it's the same.
Well, yeah, because it's used. What we're supposed to do, because this is being raised to a power, this is when you actually multiply.
Okay.
But if you had x squared times x cubed, you add those, and that gives you x to the 5th. Yeah.
Okay. Thank you.
Good to remember that stuff.
Do that.
Any questions about this?
Yes. We start from the beginning.
Okay.
Where you set it up, just like setting up the equation.
What I always have to figure out, and we might even want to draw in here, is a little rectangle to represent our radius. In this case, capital R of x. Well, I want to know how tall is R of x. So that means I need to look at what equation describes the top edge of it and what equation describes the bottom edge of it, which is what's happening right here.
Okay.
But because this is just 0, I'm able to simplify down to this. Is there a question back there?
Yeah. On your line, I see where you got the 0 and the 1. How do you know that it curves up? That's right.
Because the x squared is a parabola,
Okay.
so that's going to be a bit of a curl to it.
I
It's just an inch of
I
the
had
curve.
the other side correct.
Okay. Now, once I've established that this is R, I go back to my formula, and the volume is equal to pi times the integral from the start to the end of the region, that's 0 and 1, of the R value squared dx. Because remember, it's just like finding the area of a circle, so it's the radius value squared times pi. I'm going to add them all up.
I thought I had these.
Okay.
Where in the world do you get 5?
This becomes,
Like 2.5? I don't know.
when you take x squared and square it, you end up with x to the 4th dx. So
Oh,
then I
you
increase
raised
that
it 1 power.
Thank you. Like I said, I didn't know if I did too much in one step there or not.
Okay, no,
That's what
I
it
just...
was.
Okay, I need to make a note of that because I didn't get it.
Okay. So some of this is back to those basic integration rules that we remembered a long time ago. Most of the equations are not going to be near as complicated as what we did last chapter with. Just most of them. Questions about this?